Motion under gravity term is reserved only for the situation when the body is moving under the influence of Earth's gravitation. In that case, the acceleration due to gravity that's represented by g is equal to 9.8 meter per second square. When the body is falling down, we call it free fall. And when some body is released, misconception, I'll repeat, misconception is there. Whenever the body is released, u is taken 0. No, it's not the case. If a person is standing at rest, releases a ball, then in that case you will be taken 0. U, that is initial velocity. And if a person is standing near the window of a moving train, then in that case, if he releases, the initial velocity shall be equal to that of the train. And that goes true with helicopter and planes also while in motion. So here we are considering the body is released by a person who is in rest, then in that case u will be taken equal to 0. All the three equations that we had, now in place of a will replace g. All the equations u plus gt, ut plus half gt square, u square plus 2gh. Now when u equal to 0, then you are having only v equal to gt, h equal to half gt square, and the third one v square is 2gh. This gives you the relation t equal to v upon g. This also gives t equal to root 2h upon g, the value of time in terms of height. Then v equal to root 2gh. Also we get another form, v square upon 2g. We get different values, but here one condition is already imposed, that u was taken 0. This is the case for the body falling freely. You see, when the body is allowed to fall freely from rest, the distances covered in successive second, that is in first, that is in second, in third second, distances traveled will be in the ratio 1, 3, 5, 7, all that. And when we are taking g 9.8, then one assumption is already imposed here, that there is no force other than gravity like viscous, drag, or even a thrust is not there. Then let's now consider the body is going upward. That is second example. You see, it's the best example of a straight line motion, motion under gravity. Not only straight line motion, this is also the best and simplest example for uniformly accelerated straight line motion. Now the body is thrown upward. In that case, if the body is going upward, obviously this acceleration, which is always directed towards the center of the earth, body goes upward, so it becomes negative. It is said that while going upward, g is taken negative, while returning, g is taken positive. It doesn't mean that g changes anywhere on the way. It's simple that direction of the motion of the body changes. That's why these plus and minus sign. One more thing at the top. Somebody asked what is the value of g on the top. There's no change in g. Actually, same earth, same object. Then g remains same everywhere throughout the motion. Suppose you are using the relation for upward motion, then g is taken minus. It becomes in place of plus gt, it will be minus gt. In first equation, u minus gt. In second, ut minus half gt square. In third, u square minus 2gh. So all the equations are modified by changing plus sign into minus sign. When at the top, the velocity becomes 0. Whenever the body is thrown at the top, the velocity would be 0, then only it will start returning back. But what is the value of g? There at the top, same as it was below, it will be on the way, and that is the value at the top. In motion under gravity, the time taken in upward journey is equal to time taken in downward journey. Here one point is to be kept in mind, that if there is air, the time taken in upward journey would be less because of the upthrust. Second thing, when the body returns with the same speed, but the direction is opposite, so we might call it returns with equal and opposite velocity. Again, if there is air, the body will return with a little decreased velocity. Then what is the total time of flight? The body is thrown with velocity u, it will return in time in one-way journey will be equal to u by g. By using this relation, you can derive in one step. You see, final velocity there becomes 0. That gives you the value t equal to u upon g. Return time will also be same. So time of flight, you might say, becomes equal to 2u upon g. Similarly, if you use third relation, this one from bottom to the top of the journey, it again becomes 0, and you find h equal to u square upon 2g. One very important result you should remember, and if you are keenly interested, you can go ahead for the derivation also, that suppose the body is thrown from here. Body is thrown, it appears at a particular point while going upward after time t1. And after time t2, it is again at the same point while returning. Then the total time of journey shall be equal to t1 plus t2. I'll try to make it crystal clear by just giving an example. Suppose at 0 second the body was thrown upward. At 3rd second it appeared at P, and at 5th second it appeared at P. That means when 2 times appearance is quoted, it means once while going upward and the other time while coming downward. Then the total time of journey, you can directly say, will be equal to 3 plus 5, that is 8 seconds. Now, one very important thing, and sometimes which appears unbelievable, I'll tell you, you must remember it by heart, and I hope that you'll remember it throughout. What is that? If a body is thrown upward with any velocity, howsoever fast, howsoever greater it is, but you see the distance traveled in the last second shall be equal to 5 meters. This is a wonderful result of motion under gravity, that body in upward motion will always cover the distance 5 meters in the last second of its journey. How is that? That you can prove it by this method, that total time here is taken, that is equal to root 2h upon g. By putting this, you can say the last second distance traveled will be equal to g by 2. h t equal to u plus half a 2t minus 1. This is the formula for distance traveled in tth second. The body is thrown upward with velocity u. This should be g minus half g. And what is the time in going up to upward? This will be 2. T is also equal to u upon g. By this relation here, we have given t equal to v upon g, this thing. So since the starting is here with velocity u, it is going to be u upon g. You put this here, minus half g to u upon g minus 1. You just solve it, you are going to get it equal to g by 2 only. The distance traveled in the last second of upward motion is always g by 2, that comes roughly equal to 9.8 by 2, that is 4.9, and approximation is there while saying 5 meters. but this is very correct that the distance traveled in the last second of upward journey is always g by